All right, I had a question yesterday about, how do you calculate oxidation states? Oh, well, we'll do it later. But today I just want to talk about this other stuff. We could
Can you go with number 55 on the homework?
what was number 55?
Okay, I'm getting that now.
Well,
Anyways, I turned in the paper. I turned in the paper.
okay. Well, chapter 14, we're talking about the Arrhenius equation, which is this. This is an Arrhenius equation, just describes this curve. You know what this curve is called?
Boltzmann's.
Yeah.
Oh, jeez.
Boltzmann,
Yeah, Maxwell Boltzmann or Boltzmann. Different ways we could solve this equation, but solving this curve is difficult to get the A and the EA from the curve. But if we do this, if we write this equation in a different form, we got the ln of k, which is equal to minus EA over R, 1 over T, plus ln of A. Then it's easy, because here, you know, to mathematically fit this and get all this other stuff is difficult. But if we plot the ln of k versus 1 over the temperature, then we can get it easily, because at the intercept we're going to get ln of A, and the slope we're going to get minus EA over R. And so we can get this. This is if you have multiple points. You know, and we want a lot of points, that way we can average it out. But essentially what this says is, as the temperature increases, you know, the rate constant gets bigger. In other words, as the temperature increases, the rate constant gets bigger, the rate of reaction should be faster. Okay, if you have multiple points, this is the best. But what if you only have 2 points? Well, all you need are 2 points to define a line, right? And so this is a 2-point, you know, analysis. If you only have 2 points, then the common trick is what you saw or might remember of the Clausius-Clapeyron equation. Did we talk? I don't know if we did that. Clausius-Clapeyron equation describes the vapor pressure curve. The vapor pressure curve like this. Anybody remember the Clausius-Clapeyron? Clausius-Clapeyron is for 2-point analysis also. Well, this is vapor pressure versus temperature. It's non-linear. Do you remember that? This is vapor pressure of a liquid, like water. In fact, vapor pressure of water looks like this curve here. And you could describe this curve as well as by an equation that's kind of similar to that. But the Clausius-Clapeyron equation says that the vapor pressure at temperature 2 over the vapor pressure at temperature 1, this would be 2, 1, is just equal to minus delta H of vaporization over R, 1 over T2 minus 1 over T1. And Petrucci does that thing where he doesn't like negative signs, so he flips that. Well, the trick here is the 2-point. This is common. You take ln of k at temperature 2 minus ln of k at temperature 1. And so ln of k at temperature 2 is just minus EA over R, 1 over T2 plus ln of A. And so that's K2 minus K1, which would be minus EA over R, 1 over T1 plus ln of A. What this does is we can use the property of logs here. So when we subtract them, we could just take K2 divided by K1 here. And this is going to equal, looking at this, the ln of A's will cancel, and that leaves us, and we'll factor out the EA over R. So we get minus EA over R, 1 over T2 minus 1 over T1. This looks like the Clausius-Clapeyron equation, you know, with vapor pressure of a liquid, but, you know, it's different. This is for the rate constant here. And so if we only have 2 points, then we need to know the activation energy. But if we know the activation energy, we can figure out, how the rate constant changes with temperature, as long as we have the activation energy and a rate constant given at one temperature. And so there's a question on the test, there's a rule of thumb in chemistry, and that is, if you increase the temperature of a reaction by 10 degrees C, how much faster does the rate go? Have you ever heard that? A 10 degrees C temperature increase results in a doubling of the rate of the reaction because it's nonlinear. It goes. And so, does that rule of thumb work all the time? No, it doesn't. In fact, that rule of thumb is good for cooking. Like a pressure cooker. A pressure cooker, will increase the temperature because water will boil at a higher temperature, and that's going to rapidly increase the cooking speed. Or you have low altitude cooking directions. Low altitude cooking directions is you have to increase the cooking time because the temperature of water boils a lot lower, so it takes a lot longer to cook stuff. And so that's always a good rule of thumb for that, because in order for that to be the case, well, we have to select a T1. We select T1, and then we double. If we want to double the rate, then K2 is equal to 2 times K1. K1 cancels. That gives us ln of 2 over here. So in order to double it, well, it depends on the activation energy and, your initial temperature. And so we pick initial temperature. If we pick initial temperature of room temperature, then, in order for the rate to double with a 10 degrees C or 10 Kelvin temperature increase, then the activation energy has to be like 60. I forgot the number, but it's around 60 to 70 kilojoules per mole. 60 to 70 kilojoules per mole, is that even a covalent bond? Is that enough energy to break a covalent bond? Well, what do covalent bonds range from? Covalent bond energies range from
300 something kilojoules.
Yeah, it's about 300 to 1,000 kilojoules. Some weak ones, some of the weak ones would be like 100, like iodine. Iodine's so weak it could be split by light, just visible light. The peroxide bonds can be split by visible light. Those are very weak. Those are in the 100. But if you think back, hydrogen bonding interaction is 25 kilojoules per mole. So 67 kilojoules per mole is just probably denaturing proteins, causing them to unfold and that kind of stuff. But it's not really breaking bonds. I'll get to your question in just a second. And so the activation energy here is extremely low, but the normal reaction, breaking normal covalent bonds, that rule is going to fail. You're going to need a lot bigger temperature increase that causes doubling of the rate of the reaction. But I thought I'd talk about that because that was a kind of a tricky question on the practice test. Kelly?
Okay, number 55 was what I don't get is that the book says that the book converts the they just leave the half-life as is and took the Ln. Like, why did they do that? Why didn't they just directly do K1 over K2 or something?
Well, because the time is always inversely proportional to the rate. And so, all the other things being constant, you could just flip. Like, for example, we know that K is this is for first order only. For first order reactions, K is equal to 0.693 over T. And so if we ever take a ratio of K2 to K1, then that's just going to be the same as going T2 over T1. Is that right? No, T1 over T2, sorry. Because they're inversely. The faster the rate, the shorter the time. And so these two are equivalent because the 0.693 will cancel here. And so when you do a ratio like this, if I take the ratio of K2 over K1, that's exactly the same thing as the ratio of T1 over T2.
I know, but I took the ratio of the case for when it's 10 minutes and when it's 46 minutes. And I got 1.53, but the other's positive, and the other is negative. I just don't know why. Like, what do we use? Anyway,
I'd have to read that question.
yeah, number 55.
55.
I'm gonna read it out.
I need to bring this up.
I got part A, but I was struggling with part B.
All right, let's take a look at number 55.
This one is a plug and play. It would be in the part A. Just one of those ones where you flip it out, so first you find the constant, and then you find the temperature from the constant at a different time.
Okay. Is this the Arrhenius equation problem?
Yes.
So, we could do, to make an Arrhenius plot, we want multiple points, but if you only have 2 points, we can just do this, or if you can give them the activation energy, we can just do that. 2 points though, you always suffer the risk of a random error screwing things up and leading to a large. And so you're going to lose some accuracy due to random error with only 2 points. Multiple points is always better because you can do that. So chapter 14, number 55. Real quick, and then just see. How many people got number 55? You got it, John?
Only one people?
All right, the first order reaction, A yields product has a half-life of 46.2. So they give us data here, so we know what the half-life is. T1 half equals 46.2 minutes at 25 degrees C. And so here we know, this has got to be first order, so we know K, because if we have T1 half, we can easily solve. So we have K1 at T1. K1 at T1. And then 2.6 minutes at 102 degrees C. So it's a lot faster at 106 degrees C, this whole reaction. And so this is basically, this is going to be K2 at T2. Do you see? So we have K1 at T1, K2 at T2. Well, the only thing that's missing is the activation energy here.
Ah.
So maybe they're asking us, are they asking us to solve for the activation
Part A,
energy?
and then the part B, you just
Okay.
want to go to a different time and time.
Okay, once we have the activation energy, then we can solve for the half-life or the rate constant at any temperature, because all we need is EA and one half-life at one temperature. And so what did you get for your activation energy?
34.8 kilojoules per mole.
What was it?
34.8.
Okay, 34.8 kilojoules per mole. Okay, and then,
I didn't get part B.
Oh, the only trick to that is you have to switch it back to moles for the rate for the R.
okay.
Yeah, but
Well,
that's not really a trick.
all right, so how do you do this? For part B, we have to just pick one of these. We don't know which one's more accurate, and it doesn't matter which one we pick, because both will give us the same answer. And so what we do is we just do ln. Okay, we can do this. We'll just do ln of K2 over K1 is equal to ln, well, K2 is 0.693 over T1 half 2. And then K1 is 0.693 over T1 half 1. You don't have to substitute. We can do 2 separate calculations for this, right, to calculate K. But we might as well just do this. This is going to give us T1 half at temperature 1 divided by T1 half at temperature 2. Okay, then we have EA, right? And so this is going to be minus, well, I'll just put it in here. We'll just put in minus EA here over R. We've got to make sure the units work out. Now, what are the units of R? The units of R are joules per mole Kelvin. The units of EA are kilojoules. So the units won't cancel out. So you're going to have to multiply this by 1,000. So 34,800 joules per mole.
Okay, why is it negative EA over R?
It's the point, the equation.
That's because the curve. Why is it this curve like this? That's just empirical. This is based on experiment, you know. Actually, that if you go back to chapter 6, they do a little experiment where they shoot gas molecules through 2 rotating shutters, you know, and then they can get the speed distribution of the gas, and then it maps out as the Maxwell-Boltzmann. It's seen there. It's seen when we go to chapter 19. It's seen when we're talking about the Boltzmann equation and the energy states, how they're populated. Did I talk about this? The population of the energy states follows the Maxwell-Boltzmann or the Boltzmann distribution kind of thing, you know. As the temperature increases, it shifts the population up. Anyway, this is 1 over T2 minus 1 over T1. So all we have to do is pick one of those as our T1. So pick one of those and put the temperature in here. And then what we want to do is we want the half-life to be 10 minutes.
Professor,
and so
it's T1 minus T2, if that makes a difference.
T1 minus T2?
Yeah, I got that from the book.
T1 minus, oh, okay. I know the book, oh, okay, Petrucci likes to do this. Petrucci doesn't like this negative sign here.
It's exactly what they did. There's no negative in front of the
And so Petrucci will multiply by -1,
which flips this.
which flips this. T1 minus T2. I don't like that. I don't like that because, you know, when I'm thinking about logs, this is K2 over K1. K2 over K1 is going to be 2 minus 1, right? Always 2 minus 1. And so if I have K2 over K1 in the log, then I want to see T2 minus T1. I don't want to see T1 minus T2 because I just memorized, you know, the property of logs. And so Petrucci will do this. He does this in the Clausius-Clapeyron too. In the Clausius-Clapeyron, he has plus delta H vaporization, T1 minus T2. I have a preference to do final minus initial always, not initial minus final, just to get rid of the negative signs.
But what's precisely K1 and what's precisely K2?
K2 is the unknown. This is K2 is your unknown. K1 has to be a known. You just pick one of those.
Yeah.
And then plug it in.
But what if both of them are known?
No, both of them aren't known because this. What is the temperature with a half-life of 10 minutes? You know that okay, let's do this. The half-life is 3 minutes at 106. The half-life is about 50 minutes at 25. And so how long, well, with a half-life of 10 minutes, what would the temperature be? Well, it's going to be between 25 and 106. Where exactly? I don't know, I just guesstimate. Let's guesstimate where that temperature would be. And so at 10 minutes, where would you guess the temperature would be? Just guess. This will be a strategy for multiple choice, you know, to save time. Save time on multiple choice, you just do these kind of little guesses or whatever else. What?
50 degrees C.
Okay, there you go. So you guess 50 degrees C, it's somewhere between there and there. But we don't have to guess because, you know, we have time and we could just plug in the numbers into the equation. We plug in the numbers into the equation, we'd be done with it. So you just plug in the numbers here. You know, I just picked okay, 10 minutes is T2. So this is unknown. But T1, we know one of them. Let's just do 2.6 minutes for T1. And then this would be at 106, so that would be 379 Kelvin. Okay? And then just solve for the unknown. This is one unknown.
Okay, so the half-lives are known, and if I convert both to K, both K's are known.
Yes.
if both K's are known, which one's K1, which one's K2?
They want 3 Ks. You know 2? There's one more K that's missing. They're asking for 3 K values, not just 2. Because if they're only asking for 2 K values, we have it here. They're actually asking for 3 K values.
What's the third one?
The third one is this one, at 10 minutes. At 10 minutes, the K, this is the K3 we're gonna call it, is 0.693 over 10 minutes. This is the third K value. And so it's actually 3 K values that they're asking for, not just 2.
Wait, if you
Well,
divide that, you
but
get the third.
actually, we'll go through it step by step, but we'll do that like right after class. I'll go through it step by step, and so I don't skip any steps. And so let me talk about this right after, because I gotta talk about chapter 19 next. I just want to finish up chapter 19 today. We barely have anything left in chapter 19 actually, and so let me just talk about that right after class. So basically, you have to put yourself, whenever you do a thermal calculation, you have to ask yourself, is it standard or non-standard? And then you have to ask yourself, is T equal to 298 Kelvin or not equal to 298 Kelvin? And that's going to, that's the first thing you ask, because the equations will be different depending on if it's standard or non-standard, or if the temperature is different than 298. And so when we're dealing with standard conditions, then we have a choice. The temperature might be 298, the temperature might not be 298. But what does standard conditions mean? Standard conditions means that, the concentration of all, this is reactants and products. This is everything. You know, the reactants and the products have a concentration of 1 molar. And the pressure of any gases will be 1 bar or 1 atm. All right, and so, in other words, Q, this tells us what our Q is. What is our Q going to be? If everything's at 1, what is Q equal to? Products over reactants? 1 squared, 1 cubed, 1 to the 5th power is always going to be 1, so Q is going to equal 1. Q is going to be the initial G, what would I say? G initial over little g dot 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 over A, and initial dot 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 will always be equal to 1. So under standard conditions, our Q is going to be 1, right? Under standard conditions. So what are the equations that under standard conditions, these are the equations that we're going to do. Delta H naught, there are many ways to determine this at 298 Kelvin. Delta S naught, 298 Kelvin. There is pretty much one way of determining this. It's just S products under standard conditions minus S reactants. Both of these are easy because we have Appendix D. Right? D. This gives us 2 ways of calculating delta G. We could use the normal form of delta G, which is delta G is equal to delta H naught minus T delta S naught. This is the second law of thermodynamics. This is the entropy of the universe is increasing as long as this is negative. And so this would be delta H naught at 298 Kelvin, delta S naught at 298 Kelvin, and T would be 298 Kelvin, and this would be done. But if we're at 298 Kelvin and we have Appendix D, then Appendix D has something else, and we could use Hess's law. for this. And Appendix D has a table.
Entropies, delta G's.
Right, but it's a delta G of what? It's weird, I can't scroll down.
What does it say next to delta H?
There are many ways of determining delta H.
Okay. Thank you.
You know, how many? Lots of ways of determining delta H, right? What's the easiest? If somebody asks you, what's the easiest way of determining delta H? What would you say? Look it up. Look it up might not be so easy sometimes because you could be searching. Because especially with these basic ones, they actually, most people do more advanced calculations, so there's just some variant of that, and so that was a pain.
Product minus reactant, so rate of formation is the middle.
Well, probably the easiest way to determine it is by using Hess's law on the delta H's of formation, right? The sum of the delta H's of formation of the product minus the sum of the delta H's of formation of the reactants. Probably the hardest way. What would the hardest way of determining it be? Probably the hardest way would be bomb calorimetry, which would yield delta U, and then having to convert delta U into delta H using warp calculation, right? That would probably be the hardest way. Calculations was good. Delta S, we're only going to calculate one way, although there's other ways. So for example, for phase transitions, is the phase transition at 298? No. Oh, I mean, if the phase transition's at 298, then it works out quite nicely. But the phase transition, the temperature might equal 298 or might not equal 298. Right? But anyway, the phase transition is this, at the phase transition, well, let me talk about that. Sometimes we'll calculate delta H in this way. At a phase transition, the system's at equilibrium. Delta G naught is equal to 0, which is equal to delta H naught minus T delta S naught. And so sometimes we'll calculate delta H naught, which is going to equal, we'll add that to both sides. Actually, let's not use this one. Let's use this one. Although you can see with thermodynamics, you have to be careful here. But we're going to talk about this when we look at different temperatures anyway. And so I'm going to come back to that. We're going to use this one. It's going to be delta S is equal to Q over T. And so if Q is under certain restrictions, we can call that delta H. So delta S is equal to delta H over T. And so at phase transitions, we can calculate delta S if we're given a delta H and the temperature, or we can calculate the delta H given a... Yeah, this would be under standard conditions, but phase transitions are tricky, so there's going to be restrictions to these as well. What do we do with temperature? Is it really under standard conditions? We'll talk about that. Okay, going back to Appendix D, let me just show you. Appendix D is next to the delta H of formation column, we have a delta G of formation. And so let me tell you that probably the easiest way of calculating delta G is by using delta G's of formation, just like delta H. And so if we use delta G's of formation, we just take the sum of, nu, they call this nu, which is the moles of a product. And so this is just the coefficient, the molar coefficient there, times the delta G's of formation of the products, minus the sum of mu of the reactants times delta G of formation of the reactants. And so this calculation is pretty much the same as your delta H calculation using delta H's formation. And so this is actually a very easy way of calculating delta G. Probably easier than calculating delta H and then delta S, because this involves less work and it's faster. Except the restriction is it's only under standard conditions at 298 Kelvin. And so the preferred method is this. Now both of these should yield the same answer, but oftentimes they don't. They're slightly off. So if I calculate my delta G naught at 298 using this, and I calculate my delta G naught by calculating delta H naught and delta S naught, I'm going to see that they could be off slightly. Sometimes due to round-off error, sometimes due to slight experimental errors in the determinations of delta H and delta S.
Two questions. What is that one over there?
What's that symbol right there?
Which one? This one? This is supposed to be delta G of formation.
And then,
Okay.
how did you get the delta H naught is equal to T over delta S naught?
He just rearranged it.
This is an equation from the book. Delta S is equal to Q reversible over T.
It shouldn't be delta S.
Hmm?
And delta H. I mean, delta H is equal to delta S times delta T.
Oh, I see what you're saying. If I rearrange it, T delta S, yeah. Delta H is T delta S. Yeah, sorry about that. I mean, which is the same thing we get from this, but this is the actual derivation from the book. All right, that's at 298 Kelvin. So what this just tells you is, what would this tell you? Okay, if delta G naught at 290 Kelvin is greater than 0, it tells you what? Which direction should this reaction go? Okay, now this is getting in a little deeper because I'm going to push into the next section. But it tells you the reverse is spontaneous, right? In the reverse, then the reaction wants to shift left. That means we have too much product, right? If we have too much product, Le Chatelier say we shift. And so this says Q is greater than K. That's what it says. If delta G naught at 298 Kelvin is equal to 0, then this is telling me it's at equilibrium. There's no change, so Q is equal to K. That is, how many reactions will have a K of 1? How many, can you think of it?
Not that many.
Not that many. It's kind of rare, right? And so it's not often the case here. When delta G naught at 298 Kelvin is less than 0, then we don't have enough product. We need to form more product. There's got to be a driving force to the right. And so this says that Q is less than K, and we got to shift it to the right.
But how is delta G naught related to Q and K?
Well, the not sign. The not sign tells us what the concentrations are and the pressures are. Q, let me say this. For solutions, it's this. For gases, it's, I should do it the other way. Let me talk about Q in more detail now because we're going to go non-standard conditions. Oh, actually, before I do that, let's do delta G. Let's do, what are we doing? We're doing standard with a temperature not equal to 298 Kelvin. Right? Temperature not equal to 298 Kelvin. And so what we do here is, well, if the temperature's not equal, we're doing standard conditions, so that stays the same, but it's at some generic temperature T. And so delta G naught at temperature T is equal to delta H naught at temperature T minus T delta S naught at temperature T. And then we might go, well, you know, I want to do it the easiest way. The easiest way is, can we just say that this is going to be close enough to the sum of mu, the product, times delta G naught of formation at 298 Kelvin of the products minus the sum of mu, the reactants, dot, dot, dot. Is that okay? Why not?
That's standard temp on the right side.
There's no such thing as standard temp. It's at 298 Kelvin. It's at 298 Kelvin. Well, isn't it close enough? No, it's not close enough at all. Because delta G naught changes. In fact, it could change the sign, you know, in addition to the magnitude by temperature. And so this doesn't work. And so what we need is this, but what we could say is this. We could say that it's going to be roughly equal to delta H naught at 298 Kelvin minus T delta S naught at 298 Kelvin because delta H and delta S do not change much with temperature, right? And so not much change as long as the phase is okay. And so, we'll just say fairly independent of temperature. Okay. Yeah, I mean, it's going to change, but it's going to lead to an error. But oftentimes we don't have the delta H and the delta S at the temperature, desired temperature. So we can do calculations with this. Did we do a calculation where we figured out where it went spontaneous to non-spontaneous?
Yes.
Yeah?
It was at various temperatures.
Okay. Let's see. Let's just try a quick example here of something. Let's say that delta H naught at 298 Kelvin is equal to plus 153 kilojoules per, I'll just leave it per mole. And let's say that delta S naught at 298 Kelvin is equal to minus 113 joules per mole Kelvin. Okay. And so we see, okay, what is delta G naught at 298 Kelvin? Well, that's not too difficult. Delta G naught at 298 Kelvin is just delta H, 153 kilojoules per mole. T would be 298, so minus T would be 298 Kelvin times this, which would be a minus 113. We'll convert that into kilojoules, so 0.113 kilojoules per mole Kelvin. The Kelvins cancel, and that gives us kilojoules per mole as our unit. And so what does this come out to here? What is it? 186.674. We'll just leave it. It's 186.6 here. Kilojoules per mole. Plus? Yeah, plus. Oh, yeah, plus, which means that this is non-spontaneous, right? And so one way of visualizing this is that, you know, this means that Q is greater than K or less than K. Q's got to be greater than K because we need to go backwards, right? But you know what? I want to adjust the temperature. And so this is what I'm going to do. At what temperature can I make this go spontaneous?
How is Q greater than K?
Oh, how is Q greater than K?
Hey, let me look back.
Yeah.
Because delta G is greater than 0.
Well, this is just a primer. This is a warm-up to going to non-standard conditions. So we'll talk about Q and K in detail in just a minute. And so at what temperature can this be made spontaneous? Well, what we're going to do is we're going to try to make delta G naught at temperature T equal to 0. And so what we're trying to do is we're trying to do this. We're trying to figure out at what temperature will K, the equilibrium constant, equal 1. You know, because the equilibrium constant changes with temperature, right? And so if we can make the equilibrium constant 1, then under standard conditions, this will be at equilibrium, correct? And then I can just further change the temperature to make it go the other direction. Does that make sense or not?
Yes. Yes.
Well, because I'm actually, and so anyway, what we want to do is we want to make delta G naught at temperature T equal to 0. This is going to equal delta H naught at about equal to delta H naught at 298 Kelvin minus T delta S naught at 298 Kelvin. And so we just calculate the T. The T here is, we'll just add it to both sides. It's just going to be delta H naught at 298 Kelvin divided by delta S naught at 298 Kelvin. Is that right?
Yeah.
All right, so let's go ahead and plug it in. This is going to be 153 kilojoules, and then we did 0.113 joules, kilojoules per mole Kelvin. Moles cancel out, kilojoules cancel out, that gives me Kelvin, and this comes out to what? Negative 1,353.9. All right, and so basically what this is saying is this. This is saying that delta G naught at temperature T is equal to, what was the delta H again? 152 kilojoules? 153 kilojoules minus T delta S. Delta S is minus 113 joules mole Kelvin. Okay, what this is saying is this. You know, this is unfavorable, so I need some kind of temperature here to cancel out this unfavorable thing, right? And so what temperature is that? Well, I got to make that bigger. And the temperature comes out to negative. Okay, oh yeah, 0.13.
That's not possible.
But you go, well, the calculation's correct, isn't it? A lot of people say, I did the calculation right. I did the calculation right, and the temperature I got was negative 1,353 Kelvin. So why don't I get any points for this? And I said, no, you aren't going to get much. I'll give you a little bit of partial credit, but that's it. Because what? Yeah, this is below. This is impossible. It's impossible.
But I did the calculations right.
You did the calculation right, but this is the problem with thermodynamics. Is thermodynamics doesn't have something that says a warning, you're using the wrong equation, or warning, you're interpreting the number wrong, you could go ahead and do the calculation, but and the calculation's right, but the temperature, this is impossible temperature, so what we say is that this is non-spontaneous at all temperatures. Whereas that other reaction we did was we could change the sign, with temperature. This one, we cannot change the sign with temperature. It's impossible. And therefore, this is non-spontaneous at all temperatures, which makes sense because the energy is going up and the entropy is going down. That's not what we want, Neither of those is what we want. Well, this is starting to get into thinking about Q's and K's and this kind of stuff. Well, it turns out that under non-standard conditions, let's do that. So we go to non-standard at 298 Kelvin. Under non-standard conditions at 298 Kelvin, then we have this equation. Delta G under non-standard conditions is equal to, this will be at 298 Kelvin, is equal to delta G under standard conditions at 298. And then we'll just correct it. And you can see the correction how it's derived, by looking at how temperature impacts certain things. But this is just the given. This is just the equation for non-standard conditions. Is we'll take the standard and then correct it here by RT, ln, and Q. Now Q, if we're under standard conditions, we know what the Q is. The Q is 1, right? Under non-standard conditions, the Q doesn't have to be 1. A Q can be anything we want. And what Q is Q is called the thermodynamic reaction quotient. The thermodynamic reaction quotient is Q is equal to the activities of the products raised to their respective power divided by the activities of the reactants raised to the respective power. And so if it's a solution, we plug in the molarity. If it's a gas, we plug in the atmospheres. If it's solid, we plug in 1. If it's a liquid, we plug in 1. And so it's going to be the thermodynamic.
Okay, so I have a question. If you plug in Q for the liquid, it's gonna always be 1, but the temperature is not at 298 Kelvin.
No, we're restricting the temperature. This is Q at 298 Kelvin. Everything's at 298 Kelvin. The temperature is 298 Kelvin.
Could the temperature be not at 298?
Well, we haven't gotten there, but we'll get there in just a minute. At not 298 Kelvin. And so that means that we could do this under other conditions. So let's take a look at an example here. An example would be H2O liquid goes to H2O gas. And so in other words, we just vaporize the water. Or, this could be called boiling. Water. All right, boiling water, this is actually a phase change, this particular process, right? And so it's a phase change, so we could use some of these earlier equations, but we know boiling happens at 373 Kelvin, correct?
Yes.
We know that. Happens spontaneously at 373 Kelvin. But we could try this. We could try doing this. That is, for phase change, we'll see that delta S of the phase change is equal to delta H of the phase change over the temperature of the phase change. Where did this come from? Well, there are 2 ways to derive this. But yeah, this came from delta S is equal to Q reversible over T. Or it could come from setting delta G equal to 0 because at a phase change it's at equilibrium. But anyway, we have this, and then we'll just plug it in. The temperature of the phase change, let's just see, is equal to delta H of the phase change over delta S of the phase change. But this has to be at the temperature T, right? But we don't know because we're solving for T. So we don't know what the delta H and the delta S, the ones that we need, and what temperature those are. And so what we're going to do is we're just going to assume that the delta H at around 298 Kelvin is okay, and the delta S at 298 Kelvin is okay. And then we're going to do this under standard conditions because this is the data we have under standard conditions. And so in other words, at what temperature does water boil at under standard conditions? Standard conditions would be 1 atmosphere, right? And so that would be called the normal boiling point. The normal boiling point of water is the boiling point at 1 atmosphere. Well, 1 bar is close enough to 1 atmosphere, so let's take a look at the normal boiling point here. Or should we correct it? Is appendix D in bar or atmosphere?
Things in atmosphere. It might be bar.
Well, it's going to be very close. All right, so what is delta H? Delta H is, you know, the product
They're at 1 bar of pressure.
minus the reactant. So it's going to be minus 241.8 minus a minus 285.8, which is going to give us 44.0. So this is 44.0 kilojoules per mole. Delta S is going to be the product minus the reactant. So it's going to be 180.8 minus 69.91. Can somebody calculate that for me? 188.8 minus 69.91. 118.89. And the units would be joules per mole Kelvin. And so we need to convert one. We could just convert the top one if we want, or we could just move the decimal. Move the decimal, whatever, or multiply kilojoules per 1,000 joules per kilojoule. Let's do that. And so what does the temperature come out to? 370.1. So we're off a little bit because we know water boils at 373. The boiling point that we get by using this is 370.1, but then again we're using delta H at 298 and delta S at 298, right? So it's off a little bit, but
So,
that's okay.
it's okay, right?
Yeah, it's okay. So what we're going to do is this. Okay, this is a phase change, and this is going to be solving for the temperature of a phase change. But what we're going to do now is we're just going to look at delta G naught at 298 Kelvin. And so what this is asking is, well, this is a liquid, so the liquid's got an activity of 1. This is a gas, so we're going to say 1 bar or 1 atmosphere. And so what we're asking is this spontaneous? That is, will this spontaneously go to H2O gas at 1 bar, 1 atmosphere? In other words, if the vapor pressure of the liquid, H2O gas, is 1 atmosphere, and the atmospheric pressure is 1 atmosphere, what do we call that? We call that boiling. Boiling is when the vapor pressure is equal to the atmospheric pressure, right?
Yes.
And so here, this would be the vapor pressure. And so, well, this we would call the normal boiling point of water because we usually reference the normal. So, in other words, we're going to do this. Is this going to spontaneously boil at 298 Kelvin? I think you already know the answer. Yeah, right? Will this spontaneously boil at 298 Kelvin? You know, and atmospheric pressure has got to be 1 atmosphere. Because if we change the atmospheric pressure, the boiling point changes, right? So we could calculate this. There are 2 ways of calculating it. Let's just calculate it both ways. What's the easiest way of calculating delta G naught? Probably the easiest way is by delta G naught of formation. So we just take the delta G naught of formation of the product, H2O gas, minus the reactant. So that would be a minus 237. And so we got minus 228.6 plus 237.1 gives us
Positive.
8.5.
8.5, positive 8.5 kilojoules. Okay, this is by using delta G's of formation.
G is greater than 0.
Do you need me to write down that calculation, or can you just see that? Write it down? Write it down. So the delta G of this reaction or process is equal to the sum of the delta G's for the product of formation of the product under standard conditions minus the sum of the delta G's of formation of the reactant under standard conditions. Okay, so we have 1 mole of H2O gas. And the delta G of formation of H2O gas I get from the table here is minus 228.6 kilojoules per mole. 228.6 kilojoules per mole. Moles cancel. Kilojoules. That's the reactant. And then for the product, H2O gas. The reactant is 1 mole of H2O liquid is the reactant. And that's going to be minus 237.1 kilojoules per mole. And that gives us 8.1 kilojoules, is that correct? Positive. And so this is non-spontaneous.
G is greater than 0.
If I had 1 atmosphere, think about what's the relative humidity today? I have 1 atmosphere of air. In that one atmosphere of air, there's a little bit of water vapor, right? Not nearly 1 atmosphere. If I had 1 atmosphere of humidity, it would be ridiculous, yeah. And so it's got to go reverse here. This Q is way too big. Does that make sense? Okay. There's another way of calculating it. Or delta G naught of reaction is equal to delta H naught minus T delta S naught. This is going to be at 298, 298. All this is at 298, right? 298 Kelvin. 298 Kelvin. Okay. So the delta H naught I calculated earlier. I'm not going to go back into that calculation because it's just Chem 1A calculation. Minus 298 Kelvin. The delta S naught we calculated earlier at 118 point, what was it? 118.9?
Yeah, 8.9.
89, 118.89 joules, kilojoules per mole Kelvin. Okay. And this comes out to, actually I need this. I need to convert one or the other. Let's convert this into kilojoules.
What one?
Yeah.
You get positive 8.5.
Positive 8.5
7.
kilojoules. Okay, no, there's a difference here. These should come out exactly the same, right? But they come out slightly different. This is often the case. And it's either got to be with the delta G's of formation, or it's got to be with this, or it's got to be with round off, a combination of those. But we aren't going to worry about it. So this is non-spontaneous, basically. And so both of these say non-spontaneous. Well, the thing is, maybe I could change the temperature. In this case, I can change the temperature, right? Because the entropy is favorable. But the favorable entropy is going up. The favorable entropy is not enough to overcome the unfavorable enthalpy. But if I increase the temperature, I can get the two to cancel each other out. And so what I do here is, at what temperature, this is going to be under standard conditions, at what temperature will this go spontaneous? All right, so what I want to do is I want to go from a positive delta G, so I want to go from a positive to 0 to negative, right, by adjusting the temperature. That's what I'm going to try to do. And so the way I'm going to do that is I'm just going to set delta G naught at temperature T equals 0. Just set it equal to 0 and figure out what temperature I need to get that to equal to 0. And so what I'm going to say is, well, I need the delta H naught at that temperature minus T delta S naught at that temperature. But I don't have those, so what I'm going to do is I'm just going to say, well, this is going to be close enough to delta H at 298 Kelvin minus T delta S naught at 298 Kelvin here. And then just solve for T. When I solve for T, this is T is equal to delta H naught at 298 Kelvin divided by delta S naught at 298 Kelvin. And this is going to give us, well, this is the same calculation we just did, except this calculation is not for phase transition. This calculation, well, it is for phase transition, but this calculation can be for any reaction, right? Not just a phase transition. So 370 Kelvin, it's off a little bit, so it's okay. All right, let's go to non-standard. At 298. Did I already do this?
Yeah, you did that.
Okay. And I did I do it not at 298?
No, we haven't done that.
Okay. All right, when we go to non-standard, not at 298, then we have to have delta G at some temperature T, which means we need delta G naught at temperature T, which is going to be plus RT ln of Q. Now, we need Q at that temperature too, but that's not a problem because that's just a given. And so delta G naught at temperature T, this is this. So can I say that this is about equal to delta G naught at 290 Kelvin plus RT ln of Q?
No.
No, this does not work. And so there are two ways to do this. Let's say the two ways of doing this are this. You could do two separate calculations. And so separate, if you do separate calculation, then the first thing you do is you calculate delta G naught at temperature T, which is about equal to delta H naught at 298 Kelvin minus T delta S naught at 298 Kelvin. And then substitute.
But how does that work?
Well, we calculate delta G naught at this temperature, plug it in here, and then calculate delta G at that temperature. Okay.
Okay.
Or we do it combined. If we do it combined, then we can do it like this. Delta G is equal to delta G naught at temperature T plus RT ln of Q. If we do this, then what we could do is we know what delta G naught is equal to. Delta G naught is equal to delta H naught at temperature T minus T delta S naught at temperature T plus RT ln of Q, which means that we're going to use the delta H at 298 Kelvin because that's all we have data for under standard conditions, minus T delta S naught at 298 Kelvin under standard conditions, plus RT ln of Q. And so the question comes up is it okay to use standard condition for non-standard?
No.
Yes, it is okay because what we're doing is we're just correcting the standard conditions for non-standard conditions, right? So we're going to have that in there. And so this is the equation.
So then is that going to be Q or is it QT? Those are the Q, right?
Yeah, these are all QTs, but Q's usually given. Now solving for T is more complicated here. And so solving for delta G is no problem. But if we solve for T, that becomes a little bit more tricky. And so here, the T calculation, let's continue that down here. T, at what temperature does delta G change sign? That is, you know, maybe it's non-spontaneous, we might want it to go spontaneous, or maybe it's spontaneous, we might want it to go non-spontaneous. And so what that means is we set delta G equal to 0 because that's where it transitions from either positive to negative or negative to positive. And so here's the transition point, or I shouldn't say, it's not a phase transition, but delta G is equal to 0, which is equal to delta G naught, right? Delta G naught, actually I needed to do one more thing earlier, but we'll do it next, which is equal to delta G naught plus RT ln of Q. But you know, this is at equilibrium, and therefore, if we're at equilibrium, Q is equal to K, right? And so I can substitute that in. And so this is going to be delta G naught at temperature T is equal to RT ln of K minus RT. Just subtract it from both sides. Okay. So we could get this. And so this shows the relationship between delta G naught and K at that temperature T.
What's that up there? Left beat. What's that to the left of RT?
Oh, negative.
Negative sign.
Yeah.
Now, if we want to solve for temperature, let's say we're out of time. So you know what I'm going to do? Let me continue this a little bit tomorrow. Or are we out of time? Or we have 10 more minutes? Oh.
15 more minutes.
Okay. I'm sorry. I was thinking.
Your hand get tired?
No, I was thinking something else. I was thinking we were done. So that's why I skipped some stuff because I was rushing through it, but I really have to skip it.
That's good then. Just move on.
All right. Let me back up, etc. And so there's more to it, but let me back up and we'll do some sample calculations from the start here. And so I was skipping some of these sample calculations, but one example is this. H2O liquid goes to H2O gas. Okay, what we can do is we can change the driving force. Delta G can be altered by one, temperature, right? By changing Q. That is, this is going to be by changing concentrations or pressures. Or by a combination of the two. So we saw we could change delta G for this reaction. H2O liquid goes to H2O gas. By changing the temperature, we increase the temperature to 370 Kelvin. Though that's off a little bit, right? It should be 373, but our calculation shows if we increase the temperature to 370 Kelvin, it should go, well, we need a temperature greater than that. It should go spontaneous, right? And then, in other words, we can boil water under standard conditions at 370. But there's another thing we could do here. We could alter the standard conditions. And we could do this at temperature equal to 298 Kelvin, or we could do this at a temperature not equal to 298 Kelvin. And so let's do the first one first. Okay, and so the question is this: how can we boil water at room temperature?
Too old to remember the dipping duck.
And so you probably already know the answer to this. How can you boil water at room temperature? You change the pressure, right? We just make sure the vapor pressure of water at room temperature, the vapor pressure of water at room temperature is like 25 millimeters of mercury. If we make the atmospheric pressure 25 millimeters of mercury, then the vapor pressure of water equals the atmospheric pressure and we get boiling. Right?
Uh-huh.
So all we have to do is we have to figure out what the vapor pressure that's required is. So we're going to do delta G under non-standard conditions, which is equal to delta G under standard conditions, plus RT ln of Q. Okay, the first thing is we're going to do this at 298 Kelvin. So all these temperatures are 298 Kelvin. And so what is Q? Usually we don't put a temperature on the Q, we just say Q. Well, Q, looking at this, is going to be the activity of the products. The products is H2O gas raised to the first because the coefficient's 1, over the activity of the reactants, H2O liquid raised to the first. Activity of H2O gas is just the partial pressure of the H2O gas. And this is going to be to the first power. This is not the vapor pressure, but this is the partial pressure, and this is 1. And so Q is the pressure of the H2O gas. So what we need to do is, well, actually, this is the vapor pressure because it's coming off the liquid. And so all we need to do is we need to make sure that this is equal to the atmospheric pressure, and then we get boiling. And so, well, let's solve for it. If we want boiling to occur, then we need delta G to equal 0 because we want it to go from positive, right, to negative. And the positive is going to be, we have to use one of those. Which one should we use? What was it? 8.1 or 8.5? Which one? 8.5?
Sure.
All right, let's use the 8.5. We have to overcome this 8.5. The way we're going to overcome it is by altering the pressure. In other words, we're going to alter Q, right? By changing Q, because the temperature is fixed, the temperature is at 290 Kelvin. By changing Q, maybe we can cancel out this here. And so this is going to be, well, let's go ahead and solve for it here. Well, let me back up one step here. And so what we want is, we want a delta G. Delta G is equal to delta G naught. This is going to be at 290. This is at 298. Plus RT ln of Q. Then we set this equal to 0, right? And so this is going to be delta G naught at 298 Kelvin, which is the 8.5, plus RT ln of K, because of this. Q equals K at equilibrium. This is at equilibrium. Okay. Well, what is K? Well, K is just the partial pressure of H2O gas, right, raised to the first power. And so this is going to equal delta G naught at 298.0 is equal to delta G naught at 298 Kelvin plus RT ln of the partial pressure of H2O gas. And then we solve this. In other words, solve this for temperature, huh? We know what delta G naught, we're solving for temperature. So delta G naught is equal to minus, we'll just do this here, I'll just show you the derivative. Delta G naught is equal to minus RT ln of K, therefore T is equal to delta G naught divided by R ln of K.
Should there be a negative in there somewhere?
Yeah, negative, yeah. And so, okay, solving for the temperature here, we can get that. Actually, we aren't solving for the temperature, I'm sorry. We're solving for K. We're not solving for the temperature. We're solving for K, which is the pressure. K is equal to E to the minus delta G naught over RT. Okay, so let's go ahead and do that. We're going to plug in delta G naught, which is 8.5 plus 8.5. I'm going to convert kilojoules into joules, so 8,500 joules over R, 8.3145 joules per mole Kelvin times T. This T is 298 Kelvin. And so Kelvin cancels Kelvin, joules cancels joules, except this is 8.5 kilojoules per the reaction as written. Per the reaction as written, it's going to be per mole of reaction, so the moles will cancel. And so what is the pressure?
Okay, how do you know that we're solving for K?
This K is equal to,
Well, we're just trying to figure out how we can alter the standard conditions, not by changing the temperature, but by going from standard to non-standard.
Are we going to solve with delta G?
No, we already know what delta G
delta
is.
G is equal to 0. That's what we're solving.
Delta G naught is equal to this, delta G is equal to 0.
30.894.
Three zeros?
No, 30.894.
30.894? Oh, you know what? I forgot
We have to change something to the bar.
the negative sign. Sorry.
Just put a negative in front of him.
What's your new number?
No, one word.
Point 0.03236.
Okay. 0.0323.
68, yeah.
68. Okay, the units on this are going to be atmospheres or bars, depending on it. Atmosphere and a bar are close, not exactly. It depends on Appendix D data.
They're in one bar in Appendix D.
Is it in bars?
Yeah.
All right. This is going to be officially in bars. In other words, this is going to be 32 millibars, or about, roughly 30 millimeters of mercury. In other words, if we could suck the air out, that is, if we can suck the air out using a pump, a vacuum pump, so we suck the air out of here using a vacuum pump, and then we get the pressure of the air in here equal to 0.032 bars, then what's going to happen? Then the water will spontaneously boil at 298 Kelvin. Does that make sense?
That's cool.
Yeah, that's cool, but do you think our vacuum pump can suck down to that pressure?
Yes.
No. Our vacuum pump is way too weak.
Ours here.
Yeah. The physics has one, but we don't, unfortunately. We don't have a vacuum pump strong enough to suck down to that. Our vacuum pump, what do you think our vacuum pump can
I don't
draw?
know.
Maybe 9/10 of an atmosphere.
What's the non-lethal level of
Huh?
vacuum?
Well, you need a powerful vacuum, right?
Non-lethal.
A powerful vacuum is required. But what we have to do, as us chemists don't have a powerful vacuum, we have to do a combination of vacuum and temperature. This is the whole idea behind a vacuum oven. Have you ever heard of a vacuum oven?
No.
A vacuum oven is used to dry things at lower temperature, especially like organics, because a lot of organics will start to burn or combust, if you get it hot. And so if you want to dry organics, you want to dry them at a low temperature. But you don't want to do it at a room temperature because it just takes too long. And so what you do at room temperature, what you do is you have this oven. This oven is like a vacuum chamber. And so you can turn up the oven temperature, you connect it to a vacuum pump, you turn on the vacuum pump, and it starts pumping. So you could dry things at like 50 degrees C, and it dries rapidly and completely. And so that's what we have to do. We don't have a fancy vacuum pump. And so what we're going to say is that we're going to do a combination of changing the conditions, i.e. pressure in this case, and temperature. And so if I were to hook up my flask to our house vacuum, how hot would I have to heat the water to get it to boil? And so I'm going to estimate this. Let's estimate our house vacuum at about a half an atmosphere, okay? Or half a bar. And so this is the next example question. At 1/2 bar, what is the temperature required for boiling water? So we want to make this spontaneous. At 1 bar, it's going to be 370. Actually, that could be part of the error too, because, at 1 atmosphere, it's 373. At 1 bar, it's probably slightly different. And so it is slightly different. For boiling water, okay, at 1/2 bar, how are we going to do this? And so what we're gonna do is we're gonna do the same thing, except now, not only are we going non-standard, we're not at 298 anymore. And so delta G at temperature T is going to equal delta G naught at temperature T, right? Minus T, RT, actually not minus, plus RT ln Q. Right? Okay, so this is going to be delta G. We want this to boil, so we want delta G at this particular temperature to go through 0. So it's going to go positive to 0, which is equal to delta G naught at temperature T plus RT ln of Q. Okay, what is delta G naught at temperature T? Was that 8.5 or 8.1? Was it 8.5?
Yeah.
That's what we used last.
8.57.
It's what we used last time, but can we use it this time?
Oh, no.
No, why not?
It's not good.
It's not at 298. That was delta G naught at 298. This is not equal to 8.5 kilojoules, right? Plus. It's not
Because
equal.
that's the G naught at 298.
Yeah, so we calculated this one, right?
Yes.
But now we got to calculate a new one. We got to calculate a new one at temperature T. But what is temperature T? Actually, temperature T is what we're trying to solve for. So does that mean that this is impossible now to solve?
No, it's hard.
It's hard, right? But not impossible. And yeah, it's
We use the delta G is equal to the negative RT.
can we use that?
No, that's just. No, yeah, you can. That's not standard.
Okay, yeah, okay, let's go with this. Can we use this equation? Delta G naught is equal to minus RT ln of K. Yeah, we can because, do we know?
We also don't know T.
Yeah, we don't know T, and do we know, well, we know K at T because it should be 1/2 bar, so we know that. We can't use that either.
Never mind.
Never mind. We can't do this one too. We can't say T is equal to delta G naught over R ln of K, right? Because of this. This isn't going to work either.
How come?
Because we don't know the temp. We're solving with the solve. Or however you want to say it.
We know that. So just solve that.
You're solving the other one. There you go.
Well, maybe I shouldn't give up so quickly. Maybe we can solve this.
What about the combined?
Just try it.
Well, actually, both of these are going to lead to the same thing, and that is delta G naught, because when delta G is equal to 0, Q is equal to K. And so we're going to have that this. Delta G naught is equal to minus RT ln of K. But we have this temperature problem here. But we also know that delta G naught is equal to delta H naught at temperature K minus T delta S naught at temperature T. And this is going to equal minus RT ln of K, right? Okay, now let's do this. We're going to add it, well, we're going to make this assumption that delta H naught at temperature T is about equal to delta H naught at 298 Kelvin minus T delta S naught at 298 Kelvin, which is going to equal minus RT ln of K. Okay, then we're going to add a T delta S naught to both sides. We add a T delta S naught to both sides, we're going to get delta H naught at 298 Kelvin is equal to T delta S naught at 298 Kelvin minus RT ln of K. Then we're going to factor out a T and then divide both sides by that, so we'll get delta H naught at 298 Kelvin divided by delta S naught at 298 Kelvin minus R ln of K. And there we have
I
it.
just don't know where he's going.
We have it because now these ones are okay at 298. K, we already know, K should be 0.5 bar, or just 0.5, K is dimensionless. And so we can use this equation to solve for T under non-standard conditions if we want to do the phase transition. Or,
That is, when you had the delta G naught of T is equal to the negative RT, okay, you got that from the regular standard, right?
no, this equation comes from this. Delta G under non-standard conditions is equal to delta G naught under standard conditions plus RT ln of Q. And then we set delta G equal to 0. Delta G is equal to 0, which is equal to delta G naught plus RT ln of K. And then just solve this for delta G naught. Delta G naught is equal to minus RT ln of K. But you know, both of those paths lead to the same equation because it's the same thing. And so this is the way we can solve for the temperature. So if I'm at a half atmosphere or half bar, K is a half bar, so we'll plug that in. We know what R is, we know what delta H and delta S naught are at 298, and then we can figure out what the temperature is that this should boil at. And it should be between 0 and 373 Kelvin, right? Stuff. Well, actually, this is the last equation of chapter 19. Yeah, we're pretty much done with chapter 19, but I'll go through some more sample calculations.
Okay, well, I want to read chapter 17, right? And, you know, I have history because I'm doing that. Yeah, so how can I ever get no clue to that? Right? But I need to study for psychology too, or review the notes for psychology too, or else I'm behind on that stuff.
Professor?
What